Hello everyone! So we are going to talk about uniform circular motion, which is still part in chapter 4, and we're only going to talk about the uniform circular motion part, and then on Monday in class we're going to do the relative velocity, so that will finish up chapter 4 for us. And then we'll work on some labs using the carts and tracks that we just got this week, and we're also going to start chapter 5, which is about forces. So let's go ahead and get started with uniform circular motion. I have attached this PowerPoint for you also as a document on your blog. So if you want, print the notes off and then just follow along and add in any extra stuff that I talk about, then I would really recommend that. If you don't print them off, then I would just get out a piece of notebook paper so that way you can make additional notes on the sides, because we're going to write the formulas and derive some things within uniform circular motion. So, uniform circular motion is the motion of an object traveling at a constant or uniform speed in a circular path. So uniform just meaning that we have this constant speed, and circular motion, we're moving in a circular path. So this could represent a rock that's maybe being twirled in a circle that's on a string that has a constant length. This could be an electron that's in orbit around the nucleus for Bohr's model of a hydrogen atom, since that would have to be my perfect circular orbit. It could be a charged particle that's moving in a uniform magnetic field. It could be a planet traveling around a perfectly circular orbit. So there's so many different examples that we can have here to describe uniform circular motion. Now, while I have uniform circular motion meaning that it's traveling at a constant speed, I want to know, does an acceleration exist for this object or for a particle that's undergoing uniform circular motion? Why or why not? So, do I have an acceleration that it will exist if an object is undergoing uniform circular motion? You will have an acceleration, because when we're moving in a circular path, there is still a constant change in direction. So the magnitude of that velocity vector is going to be constant. But because I'm changing direction, because acceleration is a vector, once I change my direction, I'm going to have some type of once I change the direction for the velocity vector, I'm going to have some type of acceleration. So because we're changing direction, we do undergo acceleration in uniform circular motion. So speed, or the magnitude of the velocity, will remain the same or constant, but direction is constantly going to be changing. Now, the constant magnitude velocity vector for us will always be tangent to the path of the object, and it's going to be perpendicular to the radius. There we go. And it's going to be perpendicular to the radius of the circular path. So your constant magnitude velocity vector, it's always tangent to the path. So if this is my circle, I'm going to be tangent to the path of that circle, and then it's perpendicular to the radius. So here's my radius, and that velocity vector is just perpendicular to the radius. The change in our velocity vector is going to be due to the change in the direction. So we already said that. The direction of the change in velocity is going to be towards the center of the circle. So our direction of change in velocity will always be towards the center of the circle. In this, we have a particle that's moving from point A to point B on a circular path. So my initial radius, Ri, is here, my initial velocity vector here at point B. I'll have a final velocity vector which should be equal in magnitude here, and then I have my radius that was the final, which those should just be the same. And I had some angle in between there. My overall displacement will be this delta R vector that's right here. So I can have a triangle that's formed with just for my displacement. So I can call this my displacement triangle, because I have my initial radius, my final radius, and overall I'm going to get some displacement vector. I have also a triangle that I can form based on the velocity vectors. So if I look at my velocity vectors, I have my initial velocity that I have represented here, and that's going to be some angle difference from the final velocity vector. The change in velocity, my overall delta V velocity vector here, is going to be pointed downward. It's going to be directed towards the center of the circle. So the vector diagram here for my velocity triangle is going to show me that the final velocity can be found by adding the initial velocity to that change in velocity, my change in velocity vector here. Okay, in terms of centripetal acceleration, for centripetal acceleration, we know that centripetal acceleration is going to depend on the speed of the object and then also the radius, which we call r, of that circular path. So we have a formula for centripetal acceleration, and that is AC, I don't know if we can see that, AC equals our velocity squared over the radius. So I have v squared over r. Our acceleration will always point toward the center of the circle of motion, and then the acceleration is always perpendicular to the path of the motion. If this were not true, there would be a component then of acceleration that would end up being parallel to the path, and then therefore we'd have a component that's parallel to a velocity vector. But since we're talking about constant or uniform circular motion, we know that that couldn't be true. So our acceleration vector can only have a component that's perpendicular to the path, and that perpendicular component is always going to be towards the center. Okay, so how do we derive, since we knew that our formula for centripetal acceleration is v squared over r. Guys, the reason we also write this c there is to differentiate that this is centripetal acceleration, not just any acceleration. We're talking specifically about circular motion, so that subscript c will denote centripetal acceleration. Okay, so we just said in the last picture, if we're looking at here, I have a circular path, and if I'm thinking about my displacement triangle, I had my radius, and then I had this displacement vector here, which just delta r. And then I also could form a velocity triangle. When I form those, I can see this here as well. This is my circular motion, my radius, my particle started here at, we'll just say position 1, ended at position 2. So the velocity for velocity vector 1 here, whenever it was at position 1, this is my velocity vector at position 2. My S is just representing my overall displacement that I have for this displacement triangle. I also can make my velocity triangle. So these are similar triangles. So two similar isosceles triangles. The radius is going to be the same, and my V1 and V2 are the same in magnitude because it's at uniform or constant motion. So since this is a constant speed, which meaning that I have equal magnitudes here for these two, then my R values are also the same. I could say that S over R is going to be equal to my delta V over V. Now, I know that this S is ultimately just a displacement. I started from one position, I ended up at this second position. And we know that velocity is equal to that displacement over change in time. So instead of writing velocity over my displacement over change in time, we're just going to write it as this particular distance here that we're interested in is equal to velocity times change in time. So before we could have said V was equal to S over T. So it would be equal to this distance over the amount of time that it took to make that particle move from here to here. But I just want this to be solved for S instead. So we did S is that velocity times time. So if I plug this velocity times delta t in for s, let's do that now. I would end up getting v delta t over r, and that's going to be equal to delta v over v. Well, how does this get me to centripetal acceleration? I know that acceleration is the change in velocity over the change in time. I know acceleration is a change in velocity over the change in time. So I have this change in velocity, and I have this change in time. So if I rearrange this, then I'm going to get, let's say I multiply this v on both sides. So that v would cancel out. I'd end up getting v squared times delta t over r equals that change in velocity. Well, now I want this delta t to move over here. So if it did, I would get v squared over r equals delta v over delta t. And that delta v over delta t is the same thing as my centripetal acceleration. So we're just going to call that AC. So that's how we're deriving our centripetal acceleration formula. Okay, we also have something that's called the centripetal force. And any motion in a curved path that represents accelerated motion requires a force that's directed toward the center of curvature of that path. We call that centripetal force. Centripetal just meaning center seeking, so it's a center seeking force. Now, force is equal to mass times acceleration. And a force is measured in the units newtons. A newton is the same thing as a kilogram times a meter per second squared. So mass, my kilograms, acceleration, I get that meter per second squared. So a newton is also equivalent to a kilogram meter per second squared. I know that if this is centripetal force, I'm going to have to write that that acceleration is using centripetal acceleration because I have to be in this constant uniform circular motion. And I also know that centripetal acceleration is equal to v squared over r. So centripetal force, which I'm going to denote that with C since I'm speaking about centripetal force is going to be mass times my velocity squared over r. Because we just derived that AC, my centripetal acceleration, is equivalent to v squared over r. So this would be my centripetal force. That would be my centripetal force formula. Now, let's say that the speed of a particle moving in a circular path doubles. What would end up happening to that centripetal force? If the speed of my particle moving in a uniform circular motion doubled, then my force would quadruple. Because if I did 2v here, that 2v would be squared, so I'd really get, it's like 4v squared. So doubling my speed for a particle moving in uniform circular motion would end up quadrupling that force. All right, the period, which we are going to denote t, is defined as the time interval required for one complete revolution of the particle. Now, during this time interval t, we know that the particle will move a distance of 2 pi r. So if we go completely in for one complete revolution, we know to move completely around that circle, the particle is going to move 2 pi r. Which would just be equivalent to the circumference then of the circle. And we know that it's going to move at a particular speed. So I know that I have some speed and it's going to be moving 2 pi r in a specific amount of time. So if I wanted to find velocity, then velocity would be the circumference that particle is moving. So I have the circumference of the circle over a certain period of time, or period. Let's just rearrange this, and then we can get the formula for period. So in this case, period would be equal to 2 pi r over v. So our formula to find period for a particle moving in uniform circular motion is going to be T equals 2 pi r over v.